So this is Advanced Higher Chemistry, and we're still looking at Unit 1, Physical Chemistry, and we are still part of the equilibrium part. And the topic for today is buffer solutions. Buffer solutions are solutions that have been specifically made in order to tolerate small additions of acid, alkali, or water and keep their pH. They're really important, particularly in the study of biological systems, but also chemical systems, where pH needs to be controlled. So the definition, which I summarized earlier, a buffer solution is a solution which keeps its pH constant when small amounts of acid, alkali, or water are added to it. Now, it's really key that you specify that it's small amounts of acid, alkali, or water, not just acid, alkali, or water in general, because a buffer solution has a tolerance limit. A buffer that's made at pH 7, if you poured a litre of 1 molar hydrochloric acid into it, would definitely change pH. It wouldn't keep it constant. They are designed for dealing with small amounts of acid or alkali or water that might get added to them over time to hold their pH in response to that, not into really large changes. So the key words are pH constant and small amounts of acid, alkali, or water. So we've got two types of buffer. We've got acid buffers and we have got basic or alkaline buffers. An acid buffer is a mixture of a weak acid and a solution of a salt of that acid, that weak acid, made with a strong base. So for example, ethanoic acid and sodium ethanoate, or benzoic acid and potassium benzoate. So ethanoic acid is the acid, and sodium ethanoate is a salt made from ethanoic acid and sodium hydroxide, a strong base. Benzoic acid is an acid. Potassium benzoate contains benzoate, so it's made from the benzoic acid. Potassium part has come from potassium hydroxide, a strong base. Now what this combination allows is that the weak acid is able to provide H+ ions or hydronium ions, if we're being more specific, to the solution because it's in equilibrium. If you add some base and that base removes some of the hydronium from solution, your weak acid is able to add extra H+ into the solution to keep that constant. The salt contains the conjugate base of the acid, and that means that if you add excess H+ ions or hydronium ions relative to the pH value that you want, the conjugate base is able to accept or absorb that H+, creating a neutral compound and therefore resist the potential change to pH. So this is a buffer made from ethanoic acid and an ethanoate salt, probably sodium or potassium ethanoate. And that combination in solution has your acid on the top left there, which is a neutral molecule. You have got the conjugate base that's coming from the salt in a high concentration. It's the negatively charged thing in the top right. And you also have the H+ ions, more specifically H3O+ ions. However, it's better in these circumstances to think of them just as protons. Now, how does this work? Well, if we add a small amount of base to the solution, small amount of base or a small amount of alkali if it's soluble, What that is going to do is it's going to remove some of the H plus ions. And if we're removing that, remember that pH is dependent upon that H plus or H3O plus concentration, and we need to keep that constant. So our acid donates some H plus into the solution and forms more of the conjugate base. And as a consequence, the concentration of H plus remains unchanged and the pH can stay constant. Now, what happens in the opposite situation? Well, what happens if we add a small amount of acid? Well, if we add a small amount of acid, it's going to increase the amount of H plus in solution. And so in order to keep the pH constant, we need something that's going to get rid of that excess H plus, and that's going to be our conjugate base from the salt. And as a consequence, that's going to form some of the neutral acid. And again, what happens is that the concentration of H plus remains unchanged and allows the pH to stay constant. So a buffer solution allows you to deal with both situations. Now, you might ask, why do you need the salt? Why can the acid on its own not just do that? Because the acid on its own will have all three components. You need an excess of the conjugate base, and that can only be present by adding a salt. You don't produce an excess of conjugate base from the acid on its own. Now, a basic buffer, well, a basic buffer is going to be the opposite. It's going to be a weak base and then a salt that's made from a weak base and strong acid neutralizing one another. So a good example would be ammonia and ammonium chloride. So ammonia is a base, ammonium is the conjugate acid of that weak base, and chloride is from hydrochloric acid, a strong acid. Methyl ammonia and methyl ammonium nitrate is another basic buffer. Again, methyl ammonia is the base, methyl ammonium is the conjugate acid, and nitrate, well, that's come from nitric acid, a strong base. Now, in this case, the weak base itself, if you add excess H plus to the solution, the base can absorb the H plus if excess is added, and the salt contains the conjugate acid, and so if something is added that removes any H plus from solution, the conjugate acid can donate and provide more of the H plus to keep the H plus constant. So we'll just see that in action. So here is an ammonia-based buffer. You've got the ammonium salt. You have got H plus concentration. Now that's always in solution. It's not coming from the base on its own. And you've got the base ammonia on the right-hand side there. So the H plus is just being generated in solution naturally. We know that pure water contains H plus ions. Now, if we add a small amount of base, what happens is that we are removing some of the H plus through a neutralization reaction in order to replenish that H plus. The conjugate acid, the NH4 plus, donates some of its H plus and forms the neutral NH3 ammonia. As a consequence, the concentration of H plus remains unchanged and our pH will stay constant. If we now do a situation where we add acid, if we add a small amount of acid, that's just going to increase our H plus. And if we want that to remain constant, we'll need the base, the weak base, the ammonia, to remove, absorb, accept that H plus, producing ammonium ions and keeping the H plus concentration constant and hence the pH constant. Now, in order to know what pH your solution needs to be, you have to use this equation. Now this equation, pH equals pKa minus the log of acid divided by salt. Now normally whenever we have Ka and logs, we're thinking about equilibrium conditions, and we'd think about the concentration of acid and concentration of salt at equilibrium. This equation, your concentration of acid and your concentration of salt are your starting concentrations, what you would actually make up before equilibrium is reached. So pH equals pKa minus log of acid over salt. You need to remember that the acid is above and you're dividing by the concentration of salt. And that log applies to the whole of that. It's not the log of the acid, all divided by salt. It's acid divided by salt, and then take the log of that. That's important to remember, particularly when you're putting it in your calculator. So the concentration of salt, concentration of acid are your starting concentrations. What happens is that if your salt and acid are the same concentration, the log, you get a value of 1. The log of 1 is 0 and pH equals pKa. So that can be a question that is asked. If you've got a buffer solution and the pH of it is equal to the pKa, what that means is that your concentration of acid and salt are the same. And acids and alkalis can only make buffers around their pKa value. So if you are needing to make a buffer solution at a particular pH, your starting point for what to use would be to look at page 13 of the data booklet for the pKa values of lots of different acids and pick one that is close in value, where the pH value is close to the pKa value. So it's mostly the questions use the equation pH equals pKa minus log of salt over acid. Acid over salt, sorry. And that equation is written in the front of your data booklet. So first question, and it's going to be a worked example. What pH will a buffer have if it is composed of 0.5 mole per litre benzoic acid and 0.2 mole per litre sodium benzoate? Well, pH equals pKa minus log of acid over salt. If we look up page 13, benzoic acid has a pKa of 4.2, and we know that the concentration of the acid is 0.5 and the concentration of the salt is 0.2. pH equals 4.2 minus log of 0.5 or 0.2, which is about 0.398, and so overall we get a pH of 3.80. And that is to 2 decimal places. I would go to 2 decimal places in relation to pH because your pKa is always given to 2 decimal places. We've now got the harder type of question, which is if you are told what pH you need to make, and then you have to work out what concentration you need to make it at. So what concentration of sodium methanoate is needed to make a buffer solution of pH 3.5 using 0.5 mole per litre methanoic acid? So again, we write out our equation, pH equals pKa minus log of acid over salt. Our pKa value this time for methanoic acid on page 13 of the data booklet is 3.75. And we know that our acid has a concentration of 0.5, so when we fill it out, we have got this. Rearranging the equation, so we're moving the log acid over salt to the left-hand side and taking away the 3.5 on the right-hand side, we end up with 0.25 equals the log of 0.5 divided by x. We need to do the anti-log, so 10 to the power of 0.25 0.25 equals 0.5 divided by x, and then we can solve for x. X equals 0.5 divided by 10 to the power of 0.25, which equals 0.2 moles per litre. That answer has been rounded to 2 decimal places. So we finish with 3 questions. I'm not showing all the working out, I've just got the answers. So what you can do is pause the video, have a go and get the answers, or copy the answers down and see whether or not you can work out to find those. So if you are going to pause the video, I suggest you pause it now. And then if that's you unpaused, here are the answers. So what pH will a buffer solution made of 1 molar sodium benzoate and 0.2 mole per litre benzoic acid have? Well, we've got 4.90, again rounded to 2 decimal places. What concentration of hydrofluoric acid is needed to make a buffer solution of pH value 3.10 from 0.5 mole per litre sodium fluoride? I got 0.59 mole per litre. And finally, we have got what concentration of butanoic acid is needed to make a buffer solution of pH 4.83 using 0.75 mole per litre potassium butanoate? This should have been the easiest question for you to do because the pH is 4.83. Butanoic acid has a pKa of 4.83. And so the only way that pH and pKa can equal one another is if the concentration of salt and acid are the same. So the answer to that is 0.75 mole per litre. You can tell if there is a trick to doing the question because it'll only be worth 1 mark as opposed to 2 or 3 marks for a question in which you would be expected to do calculations and manipulate an equation. Question 3 would only have been worth 1 mark. So this was looking at buffer solutions, and we saw that buffer solutions are made of a weak acid or weak base and a salt made from that weak acid or base and a strong base or acid. We know that buffer solutions are solutions that maintain a constant pH in response to the addition of small amounts of acid, alkali or water. And we learnt the equation pH equals pKa minus log of acid over salt as a way of determining the pH of buffer solutions. So we still have, I think, 1 or 2 more lessons to go on equilibrium before we move on to another topic, and I will catch you for that next time.